Wittgenstein High Integrity Systems presents coffee break training. Welcome to this coffee break training session from Wittgenstein High Integrity Systems. This video looks at part of the SAFERTOS API and considers how periodic tasks can be created. As with earlier videos in this series, SAFERTOS+Trace is used to help visualize the discussion. More information and additional training sessions can be found on our website. Follow us on Twitter at Wittgenstein_Hiss for updates on new training sessions. SAFERTOS+Trace consists of a user-friendly GUI coupled with a trace library to allow the user to quickly profile and optimize code, view task scheduling, and interrupt interaction. It allows for custom event logging and can help debug an application running on SAFERTOS. Today's session is going to look at part of the SAFERTOS API. Specifically, that with regard to delaying tasks or creating periodic tasks. As in previous sessions, we'll use the SAFERTOS+Trace GUI to aid our understanding of the system. This session also shows how printf-like expressions can be used to add information to the trace. Again, in this example system we have three main tasks running, one each of low, medium and high priority. However, during the period of time we'll examine in this video, the medium priority task is paused, so we only have the low and high priority tasks to consider. As before, there is also a timer-based interrupt and handler routine, but again these can be ignored as they won't affect parts of the system that we're interested in. This view shows a longer time period than we considered in the last video. Here, each alternating grey and white bar represents 10 milliseconds. The shading changes automatically as you zoom around the trace to keep it clear at all times. This is the low priority task code. The main body is a loop that runs 12 times with a delay of 3 within the loop. Each time it runs, we use the SAFERTOS+Trace logging feature to print the current loop counter. At the end of the loop, we can then calculate the time elapsed over the loop duration, again printing it to the event log. The high priority task code is even simpler. It just operates in a loop consuming CPU, with a delay of 1 tick each time through the loop to allow the low priority task to run. If this delay wasn't present, the loop would simply run continuously as this is the highest priority task in the system. The prv_busy_for function consumes more than 1 tick each time, but the low priority task will only be able to run when the xTaskDelay call is reached. The low priority task delays for 3 ticks before printing the message to the log. If we take a closer look at the first 2 loop iterations, we can see more clearly the events over each RTOS tick. What this shows is that after the delay of 3 ticks has expired, the low priority task has to wait a further tick before the high priority task pauses. This means that the low priority task is 1 millisecond or 1 tick later in executing than it desired, or another way of expressing this would be to say that it has slipped. The long-term effect of these slips is that at the end of the loop, instead of 36 ticks having elapsed to run all 12 iterations of the loop, in fact 45 ticks have passed. This slip will continue to accumulate in a running system, meaning that what we thought was a periodic task is in fact running significantly less often than designed. By making a small but important change to the code, we can solve this problem. Instead of using the xTaskDelay function, we use xTaskDelayUntil in the low priority task. Rather than having an absolute delay, this has a relative delay from when the task was previously scheduled as being in the ready state, by which we mean able to run if the scheduler permits. This is not the same as actually running. Again, the high priority task is the same as before. The initial behaviour looks similar to the earlier example. However, things change later in the sequence, so let's take a closer look. We have the initial print statement showing that the loop has run once, but as shown by the checkered part of the trace, this task has been ready for some time, just unable to run. In fact, the delay is enough that the second iteration of the loop moves to the ready state on the next tick. However, it is still blocked from running because the high priority task is running. With a delay of 3 ticks, we can see that the third iteration of the loop count would be due before the second has actually run. What we can see now is that when the high priority task pauses, in fact the low priority task runs 2 iterations of the loop on the same tick. By using the xTaskDelayUntil API call, the slips caused in scheduling the low priority tasks don't accumulate. So after 12 loop iterations, the total delay is 36 ticks. If we now put the traces side by side, we can see the trace using the xTaskDelay function appears to be more even than those using the xTaskDelayUntil. However, we know from the outputs above that the first method ends up running at a lower rate than the design appears to require. So the conclusion is that by using xTaskDelayUntil for delays, while the jitter between individual calls may be larger, over a long period the task will execute as often as expected without slip compared to using xTaskDelay. As with previous videos, the SAFERTOS+Trace GUI has allowed us to visualize the scenarios being described in a much easier to understand way than traditional debug tools. Thanks for watching. Don't forget to follow us on Twitter for details on new training sessions. If you have an idea for something that would help you using SAFERTOS, send us a tweet and we'll see if we can help.